Hello, I will be going over the physics exams from the Central Committee Entrance Exams Physics of July 21st, 2023. I will use the answers that are already in the answer sheets here and just give some additional comments to make it a little bit shorter. So this is a question of a ball in a chute, and you need to show that during its traveling here, it didn't experience any friction between the point P here and when it leaves the chute. And for this, you need to understand the subdomain C2 from the leerstof natuurkunde about energy conversion. And energy conversion is something very common in physics in many different situations. In this situation, it's related to energy conversion from the gravitational potential energy given by the mass times the gravitational constants times the height. If we define the gravitational potential energy to be zero here, and this energy is converted into kinetic energy of the ball. And if the ball if there was no friction at all, it would just means that all the potential energy here is just converted into kinetic energy, not into like heat due to friction. So that's what you have to show, and that is shown here in the uitwerking. You can calculate what the potential energy was in P, and you can also, what's given here, find out what the kinetic energy here was. And then you just have to show that they're equal. And here they use the name EZ for gravitational potential energy. That's zwaartekracht in Dutch. Okay. And B is to calculate the height y of the end of the chute above the ground. So this is what they call y. For this, from the same section subdomain, we need to know about the kinematic equations. Although I didn't see this particularly listed in the leerstof in the syllabus, but it can be found in the PINAS. Well, the more general form you need to remember is y0 plus v0 t plus 1/2 a t squared. So what you do is, in these situations, first define your reference frame. Your reference frame gives you a definition what is the plus direction and the minus direction. If these things, ball that's falling down, it's convenient to define the plus direction as downwards and upwards the minus direction. But you can do it either way. It's up to you. But what in the answer sheet they actually also defined it plus, because they give the equation y is 1/2 gt squared with g a positive number. So yeah, make sure you do this. Use the kinematic relation and then just plug in the time that's given here when it hits the ground, which is and oh sorry no, using the time it hits the ground, you can just calculate what the total displacement was. So you just substitute the time in, and then you find 1.02 meters. Again, I'm not going to repeat it in the next question, but take care of the significant figures. They're all given, all the input parameters are given with two significant figures. So your end answer, you also round, as they did here, to three significant figures. So question C, calculate the distance x. So with these kind of program motion, you decompose it in y and x. The y calculation was already done. And in the x direction, because there is no air resistance, the speed is constant. So then you just use this simple kinematic relation, that x is v times t. And you just plug in the velocity and the time that you found in the previous question. And then you find, again, all the inputs are in three significant figures, so your end answer is also three significant figures. Now, in this case, the ball is kind of captured by a card. And they also say that the energy is conserved. So read these carefully and use all the information carefully. In this case, they say no energy is lost in this process, which means that just before the ball collides with the card and right after, all the energy is conserved. And in this case, there's no change in potential energy, gravitational potential energy, because it's all on equal height. So we just say that the kinetic energy now, which means after, is equal to the kinetic energy before. And then it's just a matter of substituting this, and then with the unknown, the horizontal speed of the card, all other information is known. So the mass after is just the mass of the ball plus the mass of the card. So this is done here. So then solving for v, cannot read the letter here, but solving for the speed of the combined card and ball later, then you find 0.819 meter per second. The next question is about braking distance. And this is again in the same subdomain. You need to be familiar with work. It's definitely a concept that's used all the time. And work is basically transfer of energy due to a force. And the equation for work is the force times the displacement. And it's actually in 3 dimensions a in product of two factors, the force factor and the displacement factor. You see it since factor calculus might not be actually a requirement that people understand this in product. Definitely if you have done math, you're familiar with it. But otherwise you have to remember it's the magnitude of the force times the displacement times the cosine of the angle in between. Now in this case, the force of friction will be to the left while the card is going to the right. So that is an angle of 180 degrees. And that means there will be a minus sign. Now, so the change in energy is the work. The change in kinetic energy is the work. And so that is the final kinetic energy minus the initial. And substituting the work here, you get this is negative force times distance. And we can just substitute. So the main point is that when it's done braking at complete standstill, the kinetic energy is 0, which is the final, and the initial kinetic energy is totally given from all information. So substitute that. The force is given, and from this we can just isolate the displacement. So that is done here. Another way, if you didn't think of doing this way, there's actually another way. Since you know the final velocity has to be 0, you can use the other kinematic equation, which I also would remember, together with the other ones in the previous question. That's that V final squared is V initial squared plus 2 times A times the total displacement. This is actually from eliminating the time from the two other kinematic equations. Now, this is 0 since the cart came to a standstill. This is given. Now, the acceleration or similar, I should have mentioned. Oh yeah, so the acceleration here can be found from the force, which is given. So this is just the force divided by the mass of the cart and the ball together. So these are all given, so then we can just isolate this and figure out what delta x is. And then you should get the same answer. Question 1F. Now the chute is has a rough surface and actually the ball is rolling. And that means that the kinetic energy has now two contributions. One is the linear motion in the format we know, 1/2 m v squared. But there's also some energy in the rotation of the ball. And they already give you here what it is. So now we use the same concept that the energy is converted from potential energy into all the kinetic energy. And still we ignore the heat generated by friction while the ball is rolling, which is probably reasonable. So now we do the same thing. We say that the initial potential energy, which is here m times g times h, is the sum of these two kinetic energies. And then from that, you can just easily figure out what phi x is. Okay, question 2. It's about the central heating system. And they calculate some energy required to heat up the 1 kilogram of water for this increase in temperature. So here we use subdomain E3, which is related to temperature and heat. And that defines something like the specific heat, which relates to how much heat energy is needed to increase the temperature of that substance by a unit temperature, say by 1 Kelvin, and actually divided by the mass, so per kilogram. So this is an equation you definitely have to remember. And if you remember that, then this becomes a substitution exercise. We know the delta T is 50, and we know the specific heat of water, and this actually we can figure out from Venus. Be sure to know where to find these basic material properties like specific heat. Okay, and then the mass, since they ask per kilogram, you can just substitute 1 kilogram in here. Substitute that, the specific heat, temperature change, and then you find the amount of joules required. Now they talk about the water expansion, and that's from subdomain E10. What's it? What is E10? One moment. Actually, it should be subdomain E1 here, but item 10 describe volume changes in substance as a result of application or removal of heat. And they give some equations related to that. You can either look at a length increase for kind of a linear material. That's delta L divided by L0 is alpha times delta T, or like a volume change delta V divided by the original volume. And these are also sometimes called coefficients of thermal expansion. Okay, so then it's given, or not, yeah, or what you can read from this graph, that for this, what they call standard volume of 100 liters of water, the expansion is, if you go from 20 degrees to 70 degrees, then the expansion is 2.05 liters. And this you read from the graph. And here you might be a little bit careful with how many significant figures you keep. You can see, if you read it off here, that it's for sure this first digit 2 is certain. And you can also see that the 1/10 here is 0. That's also certain. And then whether or not it's 05 or 06, it's very difficult to tell, or 04. And so you just estimate that as a 5, and that you keep as kind of the last digit in the number, and that's kind of the uncertain digit in the number. And it doesn't make sense to keep on adding more here, since this is already uncertain. So you can say that this is 3 significant digits. Okay, so now we read it off from the graph, and in your answer sheet, just draw a line here and kind of explain why you thought why 2.05 is correct. Okay, so then we know that the expansion is 2.05 liter for 100 liters. Now in this system, we don't know how many liters we have. Actually, that's why they're asking. So then it's so there's just a proportionality problem here. We know that the delta V of the system divided by the volume of the system at 20 has to be 0.0205. And in this particular system, it's actually 7.8 liters, which is more than 2.05. And so we just need to figure out that proportionality constant. So we find 7.8 divided by the volume of the system has to be this. And then we find that it has to be 380 liters. And then finally, this is a volume, so you have to convert it into mass. So we use the density of water, which you can find in BNAS, but it's really super close to 1. So you find actually that it's 380 kilogram. So now they ask what is the volume change for the standard amount of water per degree if you increase the temperature at 70. You see, it is variable. You see that the slope kind of keeps on increasing. So the warmer the water, kind of the faster this coefficient is. The faster the rise is or I would say how faster the expansion is as function of temperature. So what you do here is on the answer sheet, just as best as you can write kind of the tangent in the point at 70. And from there, just take 2 points far apart, and you could just take the intersection with the x-axis, and perhaps even the highest temperature on the right. and then just divide these two, and then you get the slope. And according to the answer sheet, that slope is 0.0608. So which means that the volume increase per 100 liter is, and then rounded to two significant figures, 0.061 liter per 100 liter of water. Okay, so now we go to D. There's the in these households you have this thing expansion vessel, which is filled with nitrogen gas and with some membranes so that the water so that it's separated from the water. And so the purpose of this vessel is just to allow the water to expand without causing damage. And that's actually what I'm going to illustrate here. If you go from 20 to 70, because of the expansion, the volume of this nitrogen gas will go down, and the pressure will increase. So what you need to know for sure, and will come back in many exams, is the ideal gas law that says that P times V divided by T is constant. That's actually sufficient to use here. You just require that at 70 degrees and at 20 degrees, this ratio here is the same. And from that, you just write down everything you know, and the unknown is the pressure in this case, the pressure of the final state here. And in some cases, this ideal gas law is also used to related to the moles of gas, because this PV divided by T is equal to the number of moles of gas and a gas constant. So definitely remember this. And now they talk about heating, and in this case, all the heats to increase the temperature of the water is performed by a boiler with an heating element at 230 volts. And in this case, we need to use some from subdomain D1 about electricity, namely that the power is equal to the voltage times the current, and that is the say you can say the work done by the say electric field to push the current through, and that work is converted, and can talk about conversion, that electrical potential energy is converted into heat in this case, and in many cases in a resistor, or sometimes in a light bulb, some of the energy is converted into other forms of energy. So power, it's definitely a big element in physics. And then total energy and power are very simply related by power times time is energy. And that's what they're using here. Okay, then yeah, so you can directly use the heat is the power, total heat energy is power times time, and power is U times I. And in this case, for AC voltage, this U and I are the RMS voltage and currents. So it's also should be assumed here that this 230 volt is the root mean square voltage. Since anyway in AC the voltage is varying all the time by definition, and it actually only makes sense to talk about RMS voltage. So we can then find the power by the substitute power, and actually they're asking what the current is. Again, we should assume an RMS current. since everything else is given in this, because they tell us how much heat must be supplied and also the efficiency. And yeah, just remember something like the power out divided by power in. That ratio here, I think they call it eta, doesn't matter, is the kind of efficiency. So that's the 0.95 in this case. So that's used here to finally find what the current must be. Question 3 is about a metal strip, but they also, from the whole story, mention that this works as a mass spring system. And a mass spring system, there's this subdomain. It's actually, I think it's one of the first subdomains, B1, is talking about waves, but also about vibrations. And most vibrations can be kind of done based on a mass spring system. So even a pendulum, or I call it a swing, or even like some molecular forces. They all have like a restoring force that becomes bigger as you get further apart. And yeah, the mass spring system can be used to model most of these. So they also say that can be done with this case. Although here it's not a spring, but it's kind of the stiffness here, this bending of this, how do we call this, the strip, that causes a restoring force. So what they're asking to draw t² versus the mass of some rings they screw on, and that's just making a table and plotting it. So that's some skill you need to have. I won't demonstrate that here. Now, question B is an interesting question. So again, we can just assume the mass spring system, and for what you need to know from a mass spring system is that the period and the spring constant and the mass are related in this way. So a larger spring constant gives a shorter period squared. There's this also this relationship there, and this equation works for all these kind of vibrational systems. And so knowing this, it means that if you plot t² as function of m, the intercept here is where the mass is 0 or approaches 0. And then we also know that from the graph we made that here at this point there are no rings. So here is the mass of the rings is 0. So we only have the mass of the shaft. And the shaft is that thing that the kind of these rings screw on. So it means that this distance here is actually the mass of the shaft. And so what you have to do is kind of extend your graph and just read out what this is here, which was done here in the answer sheet. And they found 11.5 gram. And then in the next question, they're actually asking the spring constant. So again, you can use this uh, equation. Again, remember this. Then uh, t squared is, so there's a linear relation between the mass and then the slope, the coefficient in front of m here is just the slope of t squared versus m in the graph. So you take the graph again and you just evaluate the slope. And in the same way, try to keep the points as far apart to evaluate this slope. And then you have the slope, and then from the slope you find what c is. So c is 4 pi squared divided by the slope. Question D then. So they give here an equation for the deflection as function of the force, and well, we saw generally for these things the force is proportional to the, in uitwijking Dutch, the deviation from equilibrium, and this is kind of same relation but written in a slightly different way. But the larger the force, the larger the deviation. And determine the units. That's a skill mentioned that is required in subdomain A12, infer and check units in scientific formula. So you just, the unit, you first write this as an equation for E. So you try to write E is this, and then for each you just substitute the dimensions, like they done here. So you can see you get m squared here, and then this becomes 1. And oh, there's another division by 1, so actually all the m's cancel. No, wait. Divided by m squared. Let me see. Ah, sorry. Okay, I was completely wrong there. Forget everything I said there. This is actually a ratio mass divided by mass to the power 3. So that's dimensionless. So actually these all cancel. And so you have newtons here from the force, and you have meters from the deviation, and also meters from that the width of the metal. So you get Newton divided by meter squared. So that unit is actually Pascal. Determine the Young's modulus. Okay. Well, we already have the equation for E, so this becomes substitution work. Everything, the equation is known, and what we need to read out from the chart is the force and the deviation. So you just need to be careful and figure out what the deviation is. You need to figure out what is the size from one square in the grid. So do this carefully. And again, with this, here you see the scale. So again, what are the digits that are certain? Well, it's for sure between 0.5 and 0.6, less than 0.5. So the 5 here is certain. And then it becomes already estimating. So you'd say ends up somewhere at 7, but maybe it could be 6 or 8. So this becomes your best estimate, and this will kind of be an uncertain digit. And then substitute this all, and then you just follow what the answer sheet says here. But now we're going to clamp it vertically. Now, will the time period change? Well, from the equation for the period, we know that it is proportional to the square root of m over c, the spring constant. Now, we also know that this spring constant basically tells you the force if you know the deviation. So it's like uh, and what we effectively do by putting it vertically is that we add a gravity into the game. The force of gravity on the mass here will be down, but it will have a component towards the center. And that that means that the restoring force by adding this gravity is actually larger. So for a given deviation or displacement, for a given displacement, actually the force is increased. And in other words, that means that your spring constant increased. And what happens then with T? Well, increased spring force, spring constant will means a shorter time period. So a shorter time period, so here they say T becomes smaller. Okay, question 4 is about plutonium and about a dirty bomb made of it. Give the nuclear reaction equation for the decay of 239 plutonium. This is described in subdomain B2. And a couple of things, among others, is you need to know definitely what the mass number is of a nucleus, and the atomic number Z, which is 94 for plutonium. And this atomic number also determines what element it is. So plutonium always has an atomic number of 94. And the mass number could depend on what kind of isotope it is. And your isotope table in BNAS should be your friend. You should be very familiar with it. Let me try to pull it up. Isotopes. Here for it goes by atomic number, and it gives you the masses of all the different isotopes and other information. It also gives you the possible kind of decays and their half-life time. Okay, so back to the question here. And we just need to write down the nuclear reaction. And so the other you need to be familiar with is alpha particles. These are that's just the nucleus of the helium atom. So it has a charge of plus 2 elementary charges. And it's a mass number of 4. So 4 protons and neutrons and 2 protons. So you just then you look at the left and you see you go from 239 to 235. So you need to, if you subtract these, means you need to have something with 4. Oh, by the way, actually, what you have to do is, actually, let's do that. Go to BNAS, and then we find our plutonium, so 94, and we look at what are the possible decays of, or what is the main decay of this isotope 239, which is here. Then it's said here that it will decay in an alpha particle. and it is 2.4 times 10 to the power 4 years. It takes a long time, or the half-life is a long time. So we know it decays by emitting an alpha, and that is actually what you use to answer this question. So you know an alpha has to come off, and that means that whatever the other atom is, it needs to have an atomic number of 235. Now, alpha particle also has 2 protons in it, so it means that the number of protons was reduced by 2 to 92. So you get some element with the atomic number 92. Then go to BINAS. Don't know why it doesn't want to do that. And look for 92. Well, we're here, 93. 92 is uranium. So we have uranium 235. And of course, an alpha particle, and then energy in the form of gamma radiation. And that's also specifically given here. So you get alphas and gammas. Okay, for B, find the ratio between the activity A and the number of radioactive. Oh no, it's not fine. They give the relation. Actually, this relation is already given in the syllabus, and yeah, it makes sense that the activity is actually proportional to the number of kind of active nuclei, or the radioactive nuclei. If you have more, your activity will go up as well. And then there's another constant, the time constant, T1 half. And if you want to derive this equation, you just take the definition of activity. That's namely the change in n over time. So how many nuclei are decaying per unit time? And with some mass, you find the equation here. Okay, so what you see here is there's like a constant in between. Now, the question is, explain why you may assume that the activity is constant. Well, this number here is log 2 divided by so many years. So in a few seconds, the number of decays will be a pretty small percentage of the number of the radioactive nuclei you have, n, given by n. But yeah, so what you have to do is multiply this by kind of the time period you're talking about. So what I don't really like about this question is they don't say constant in over which time period. If you talk about a few seconds, then the number of decaying atoms is just this A multiplied by, say, 10 seconds. And 10 seconds is very small compared to 2.4 times 10 to the power 4 year. So you can say it's practically constant. But of course, over a longer time period, it is not constant. It's probably better if they would have said, why can you assume it's constant if you talk about, say, a certain time period of a few seconds or few minutes, few hours. Okay, then calculate how many grams of plutonium-239 were in the file. Okay, well, what do we know? How can we figure it out? Well, we use the equation here, and we use that we know the activity. we know the radioactivity, namely 1.2 times 10 to the power 10 becquerel, which is just 1/2. And we know T1/2 if we go to Binas, as I just mentioned earlier. So from this, we can figure out N. And N is the number of nuclei. So that's what we do first. And then they ask the mass how many in grams. So we just figure out what the mass of one nucleus of plutonium is. And how do we figure that out? Well, we go to our isotope table again. It should still be open here. 239 is 239.5216 U. And U is this basic atomic mass unit. So that's then what they do here. So the mass is the number of radioactive nuclei, and then multiplied by the mass, and the mass is 239 times 1.67. And this here, it was just rounded already. This number, of course, to three significant figure is 239, and this must be U, the atomic mass units, to three significant figures. So this is the mass then of one, and then this multiplied by the number. And of course, you need to be careful that this will give kilograms, since the atomic mass unit is given in kilograms. Then you just convert it to grams. Okay, question 4D. It talks about the radiation dose received by the terrorist's hand. Okay, well, first there's a story here that this file actually blocks almost all alpha radiation. So that cannot escape. But in some small percentage of the decays, disintegrations, actually a photon, gamma photon, will escape. Remember from the reaction, there is actually gamma photons released. And the energy of each of these photons is 0.03 MeV. So if during the flight the terrorist held this file in his hand for 1.5 hours, during the flight, which absorbed 25% of the gamma radiation. So the hand absorbed 25% of the gamma radiation. So 75% of the gamma radiation just went through the hand, and the mass is 0.35 kilogram. Then calculate the radiation dose received by the terrorist hand due to this 0.03 MeV radiation from the file. Okay. Well, first of all, in domain B2, there's also something defined called dose. And the dose is the energy per unit mass. So what we need to know is how much of the radiation energy of the gammas was received and divided by the mass of the hand. So next, how do we figure out this energy? Well, we know how many decay per second. It's 1.2 times 10 to the power 10 decays per second. And then we know that this small percentage will actually create a gamma photon. In this percentage of cases, a gamma photon will be created of that energy. And also, only 25% will be absorbed by the hand. And this is the energy per photon. And remember, 1 MeV is 10 to the power 6 times 1.6 times 10 to the power minus 19 joule. This you need to know. So that's given here. And then we need to multiply by the time the terrorist was in the flight, which is 1.5 hours times number of seconds per hour. And be careful with all the units you use the standard units, you don't use hours. Since the radiation is given in radiations per second, so we have to use seconds here too. So 5,400 seconds. And then that accumulates all to the energy during that time. And as I mentioned, then you just divide by the mass, and then you get the total dose in joule per kilogram. Okay, question 5. An hydrogen atom in an electric field. Okay, so here there's some story about a kind of modeling an hydrogen atom by a particle in a box, a one-dimensional box. And a particle in a box, it's kind of a potential where you have like a big, yeah, kind of well. They always call it a well potential, and you can even have infinite well. But let's say you have a deep well, and remember, potential and force are related. That the time, well, this might not be necessary knowledge, but basically the derivative of potential with respect to position is the force. So you can see this kind of very steep potential as a very strong kind of restoring force to the right. And here, a restoring force to the left. So the particle is kind of confined by this force. And in quantum mechanics, of course, it works a little bit different, but it is the basic idea. So a large potential here confines the particle and within this well. And the nice thing about this is that you can actually pretty easily calculate it. And this is one of the equations also in domain F, the energy states you have for a particle in a well. Although I think you might not need to remember it, but you kind of need to understand a little bit the principle behind it. So now they just say instead of a one-dimensional box, we have a three-dimensional cube with length L. Then they just state here what are the energy levels. So if you solve the equations for quantum mechanics that you don't need to know, but it's basically the Schrödinger equation, you will find these energy levels with 3 quantum numbers nx, ny, and nz. And they just give the energy levels here. So very similar to what they are for a one-dimensional box. And so you can basically label these states by these quantum numbers, 3 quantum numbers, nx, ny, and nz. And then also, so 1 is the ground state. So 1, 1, 1 means all these n numbers are 1. That is the lowest energy state, the lowest state. And then you might have many higher energy states. Then explain that the first excited energy level of the box consists of 3 degenerate energy states. Well, what does degenerate energy states, what does that mean? It means you have multiple states with the same energy. Okay, well, so we are in this ground state 111. So how can you increase the energy? Well, you can increase it actually in three ways. You can increase this to 2, or you can increase this to 2, or you can increase this to 2. You can have three different ways, but the sum of these squares here in all cases will be the same. That means that you have degeneracy of 3 for this excited state. And that's the answer here. So 211, 121, 112 all have the same energy. Okay, so now we're going to do something interesting. We are going to apply an electric field. And this is done along the x-axis. And the energy changes. The energy levels actually change when you do this. And the given here. So you have a ground state. You still have a ground state, but then these two excited states split into kind of two energy levels. And this energy change does not depend on Ny and Nz because the field is directed along the x-axis. Explain why after applying of the field, two states are still degenerate. Well, that's basically what they say here. They say that the energy change does not depend on Ny and Nz. Then calculate the smallest wavelengths of the spectrum associated with the energy diagram of 1b for the situation with an electric field. Okay, so the smallest wavelength, what does that mean? It means the highest frequency. And what does largest frequency mean? It means the largest energy difference. So basically, the larger the energy, the larger the frequency, the smaller the wavelength. And they want the smallest wavelength, so we need to find the largest energy difference. So let's look at all these transitions. You can go from ground state to this first excited degenerate state. But obviously the bigger difference is if you go to the one state here with Nx is 2. And that's basically the biggest step you can make. So the largest energy difference is between the ground state of 9.7 and this state with Nx equal to 2. And that difference is 19.9 minus 9.7, which is 10.2 EV. And 1 EV is 1.6 times 10 to the power minus 19 joule. And so that's the energy. But then we need to figure out the corresponding wavelengths. And then we can just isolate lambda from here. So you get this equation here. Lambda is h times c divided by e. And we substitute everything we know. And then you find the wavelength is 1.2 times 10 to the power minus 7 meters. You can also have a look at the wave functions. Then they say the wave function of the ground state in the absence of electric field is given here. Then remember, these are probability distributions. So the highest probability is to find it here, but it can be anywhere. Now, if the electric field is present, the wave function changes. And here they show the different possibilities, A, B, and C. And so what you need to know again from the subdomains is that a wave function represents probability. So wave function A means that the electron is more likely found on the left side than on the right side. And in B, it is more likely to find on the right side than on the left side. and C is actually an excited state. So now we just need to figure out where is it more likely this electron is, on the left or on the right. Okay, well, the force, the electric field is pointing to the right. And then one thing that many people do wrong is they forget that the force in case of an electron is actually to opposite direction of the electric field. This relation you find in subdomain 2 is the force is Q times E. So if the charge is less than 0, it points opposite. So it's only when the charge is positive, they will point in the same direction. So in other words, the E field is to the right, so the force is to the left. So what does it mean? The force pulls it to the left. That means that the electron can be more likely found on the left side. So that means that A should be the right answer here.